Question number 9. If relation R on the set ABC is defined by R equals BB, then classify the relation. So we need to say whether the relation is reflexive, symmetric, or transitive. So let's see, A equals ABC, R equals BB. So there's only one element. Let's check for reflexivity. I think this one is simple. You have BB, but you don't have AA and you don't have CC. So let's write down. So since AA does not belong to R, therefore R is not reflexive. Not reflexive. So that takes care of reflexivity. Now we come to the symmetry part. So is R symmetric? For symmetry, we need to see whether if AB belongs to R, then must also BA belong to R. So in this question here, we could take AB as this. There's only one possibility. So this is AB. So AB is there, so BB. So is BA there in this case? Obviously, because it will be the same element BB. I think for the purpose of this question, let's take, instead of taking AB and BA, we'll take XY, YX. So XY, because AB already stand for some elements here. So we'll take here 4 XY equals BB. So we take this BB as XY. This belongs to R. So for this belong to R, we get, or implies, that YX, which is also BB, this belongs to R. And this is the only element here. So that means we've tested this for all elements of R. So we can say that therefore R is symmetric. Now we come to the third. So transitivity. Will R be transitive? So you have in this set the element BB only. Okay. So I think I better explain this properly. So we take, now suppose we take R equals BB, and what's the process of checking for transitivity? First of all, so because the condition for transitivity is what, if AB and BC belong to R, then you need to check whether AC belong to R. Okay, so first of all, then you have to scan the relation for AB and BC. So can you find an AB and a BC in R? So that's the first question you need to ask yourself. So can you find an AB and BC in R? So if yes, then you need to find, can you find an AC in R? So with the same AB and BC, can you find the AC that results from those in R? So if you could, so suppose you cannot find it, suppose no, that means the rule has been broken, so it is not transitive. So R is not transitive. Okay, but suppose you can find, so yes, I can find AC. Then of course you have to go back to the same question. You try for other values of AB and BC. But if all goes well, so if always you can find AC for all of them, then we can say that R is transitive. Then we haven't dealt with this other branch here. Now suppose you cannot find AB and BC. Okay, right from the beginning you cannot find AB and BC, then it will still be transitive. So no. Now why? Because, so this is the case of R being vacuously transitive or automatically transitive, because there's no A, B and B, C, so this rule will not apply to R in this case. So this is the case where R is vacuously or automatically transitive. Okay, so we'll be using the structure of checking for transitivity. So in this case, we have this BB. Suppose we take BB to be, again, for in this case, we consider the condition like this: if XY and YZ belong to R, then also XZ must belong to R for it to be transitive. So in this case, in this relation, we take XY to be BB. But then, can you find an element YZ in this question? So no, because this is all the element that's there, right? BB. So you cannot find such an XY. Or even if you could find, no, it will be what? You have to take BB itself. And in that case, XZ will be again BB, but that's trivial. So you cannot find such an XY or such a YZ, even though you could find an XY. So that means this if statement does not hold, and so you don't need to have this XY, XZ. So in this case, R is vacuously transitive. Let's write down the answer. For XY equals BB, so there exists no YZ belong to R. Therefore, if you write this clearly, therefore XZ, so it need not belong to R. Hence, R is vacuously transitive. So that's our answer. So this relation is not reflexive, it is symmetric, and it is also transitive.